Okay, next we're going to look at sections 30.6 and 31.3 together. It discusses the link between electromagnetic fields, which is a pretty reasonable thing to look at considering how often we talk about electromagnetic forces, electromagnetic fields, and electromagnetism. So we talk about electric fields and magnetic fields in the same breath, so let's start to talk about how they come together. So let's have a magnetic field that points into the page. Let's say that we have a current loop in our magnetic field. And let's ask what happens if we change that magnetic field. So we've already done this now as we've been doing Lenz's law and Faraday's law. Our magnetic field points into the page. If we increase B, then we know we're going to get an induced magnetic field. If B is increased into the page, then our induced field will be out of the page. So if we increase B, we induce a field out of page. If we induce a field that comes out of the page, then we induce a current. Imagine we're grabbing the bottom of the loop. Our fingers are the magnetic field. Finger at the very bottom points to the right. Our induced current comes around this way. That would be the counterclockwise direction. So we induce a current. And that would be counterclockwise. So what happens is, if we have a magnetic flux, we induce a magnetic field. Or if we have a change in magnetic flux. If we induce a magnetic field, we induce a current. Current I. If we induce a current I, then we've induced a potential, epsilon. So that's all really good, and that's true. But now we have to think a little bit further. What makes the current? So there's a current, those charges are moving around, but what's making them move? Well, there's only one thing that makes a current move, and that's an electric force. So if we ask the question, what makes the current? Getting those moving charges, getting the charges to separate makes the potential. Well, there's only one thing that makes current, that makes the charges move. That's an electric force. And the thing that makes an electric force is an electric field. So changing the flux must make a field, which induces a current. So making that induced field must make an induced electric field. So that's pretty interesting. By changing the magnetic flux, not only do you induce a magnetic field, you also induce an electric field, and that electric field comes from that magnetic field. So let's think about this in terms of some equations. Let's write down Faraday's law first. Faraday's law says that the induced electric potential is minus d phi, put an m on there for magnetic, dt. We also know that the definition of potential, and this came from work and energy considerations, is the electric field dotted with distance. If you put these two guys together, then the result you get is that the integral of E dot ds, the integral of an electric field around a loop, is equal to the rate of change of magnetic flux. So there's a link between electric fields and magnetic fields because magnetic flux is B dot A. So now let's think even a little bit more. If I hold an apple up in the air and I let it go, it's going to fall down, of course, because there's a force due to gravity because it's in a gravitational field. If I take the apple and I put it away, gravity is still there. So there's the same deal with electric fields. Even if I take my loop and I put it away, there's still an electric field. If I put the loop there, current will flow, but if I take the loop away, the electric field doesn't go away. So my current flow in my picture up here was counterclockwise. The current comes around this way. So the electric field must match that flow. So that shows the direction of the force. So my electric field at any point must be a tangent to that circle. And it must exist everywhere. So changing this magnetic field with the x's induces this electric field with the lines. So that's kind of neat. Now if we ask a little bit more about the nature of that electric field, because it doesn't feel quite the same as it did in the earlier chapters. In earlier chapters, we said that electric fields were made by source charges Q, and we drew all those electric field lines and we saw what the fields look like. There's no charge in this picture. There's only a magnetic field. But there is definitely an electric field. That electric field is made by the changing magnetic field. So those two fields, while they act the same, they both produce forces on charge. They're slightly different in nature, and we do call those fields different things. If it's made by a stationary, a source charge Q, then that's called a Coulomb field. And if it's made by a changing magnetic field, then that's called a non-Coulomb field. So all this happened in the 1800s. That's when Faraday did his work. Maxwell got in on things in 1855, and he couldn't let go of the symmetry of the whole problem. And he said that if a changing magnetic field makes an electric field, doesn't it hold that a changing electric field makes a magnetic field? So that's what he thought was true, and he saw that link between electricity and magnetism. And that brought him to one of his four equations. And one of Maxwell's equations, the one we'll write down, is that the integral of B dot ds is equal to mu naught times I. Okay, so this part we're familiar with. This is what we called Ampere's law. It said that we get a magnetic field around a current-carrying wire. Maxwell extended it, and he said, well, you don't only get a magnetic field due to a current-carrying wire, you also get it by changing an electric field. So Maxwell added the term plus mu naught epsilon naught. Mu naught is the permeability of free space, how magnetic fields move. Epsilon naught is the permittivity of free space, how electric fields move. So he said it's mu naught times E naught times the change in electric flux over time. So Maxwell did this because he saw the symmetry and he thought they had to be related. What you see about Maxwell's equations here is that the change, the spatial change in B, so this is a spatial part, was related to the time change in electric field. So we get something happening in space related to something happening in time. Well, those kind of equations are called wave equations. And I think it's chapter 17 of your textbook is the wave equation. So writing this equation led Maxwell to theorize that any electromagnetic wave, or that light itself was a wave made out of electric and magnetic fields, and that wave had a speed of, this was 1 over v squared. So this is a wave equation. So the result of this meant that light was an electromagnetic wave with a speed, which we now call c, equal 1 over mu naught times epsilon naught. Turns out Maxwell was 100% correct. That was absolutely true, and that was kind of a revolutionary idea. It's like the first time people were looking at light like a wave instead of like a particle, so that was really interesting. Sadly, Maxwell didn't live to see this proven. Maybe it didn't matter to him anyway. If he's like a lot of us, he believed it was true without the proof. But it was proved right by Hertz in 1888. He generated radio waves, and he was able to measure the speed of those radio waves, and he found that it was in fact equal to c. So that was really pretty cool. The next thing we'll talk about, we won't spend a lot of time. We'll go to section 31.3, and we'll see about how electric fields and magnetic fields are really two sides of a single coin. So we'll do that part next.